Okay, well, welcome back. We are into our first kind of real full lesson of Unit 7. This is one that we did in class, but I'm just making a video for it as an extra. So today's objectives involve sampling distributions for sample proportions. So finding the parameters, that would be mean and standard deviation, determining whether the shape of those distributions is roughly normal, and then calculating and interpreting probabilities based on those distributions. So just as a reminder, a sampling distribution is basically a collection of a large number of sample statistics, either means or proportions of a given sample size. So we talked in the intro video about how those are created, but the whole idea behind sampling distributions is not that we actually take repeated samples to build a sampling distribution. The idea of a sampling distribution is that we can pretty much very quickly learn what to expect. What would that sampling distribution look like if we were to take repeated samples? And the reason that can be helpful and important in statistics is that it gives us an idea of what's typical for a sample of a certain size taken from a certain population, which in turn then helps us decide whether a specific sample statistic that we get is way high or way low, or is it right about where it should be compared to what is typical for that sampling distribution. And we'll kind of look at what I mean by examples of that when we get into our example problems. So today we're going to focus specifically on proportions and what the rules are for sampling distributions, what the patterns that we see emerge for sampling distributions with proportions. So instead of having to take repeated samples over and over and over again to build this sampling distribution, we're going to look at what are the rules, what can we expect. So let's start with mean and standard deviation. So these are some formulas that are on our formula chart for statistics. Again, that is linked under resources in Schoology. If you haven't printed it or if you don't have access to it, make sure you know what's there, because it's an important list of items that you get on AP exam. So we have the mean and the standard deviation. So the mean, notice these symbols, mu p hat equals p. That means, remember, mu is mean, p hat is sample proportion. So the mean of the sample proportions is equal to p, which is basically the parameter proportion, the population proportion. So in other words, the mean of the sampling distribution for sample proportion should just be the same as the true proportion for that population, which makes sense. The mean of the proportions is the proportion. And then for standard deviation, remember that's that average or typical difference from the mean. Not every single sample is going to have the exact same proportion as the population. So that difference or that variation is described by this formula. So sigma is standard deviation of the sample proportions is equal to the square root of p, 1 minus p over n. That's something that came through lots of trial and error and discovering and figuring things out by statisticians before us. Thanks to them. So we've got mean, which is center. We've got standard deviation, which is variability or variance. So now we need to know, what about shape? So mostly with any distribution, we care about center, spread, and shape. So particularly, we want to know, how do I know if a normal model is going to apply here? Because really, normal models are really nice because we have that z-table, we know a lot about them, we have a lot of rules and numbers that describe them, we can find probabilities if it's a normal model. So this is really what we want to know. Is that distribution for that sample proportions, is it normal? So we're going to look at what we call these assumptions conditions. So these assumptions conditions are basically helping us determine whether we can use the sampling distribution to find an accurate probability. Or an accurate anything, mean, standard deviation, etc. So assumptions means that these are things I'm kind of assuming to be true, and then conditions are something I have to check to make sure that it's appropriate to continue on and find these values. So assumption number 1 is that we have a random sample. This avoids bias. I talked about that in the intro video. We need to know that we have an unbiased sample, that it accurately represents the population. Otherwise, what are we doing? We know it's going to be off. What's the point of continuing? So we should have a random sample taken from our population of interest, or at least we should be able to safely assume that the sample is representative of the population, that sample looks like the population and that it represents it well in terms of whatever proportion I'm trying to find. The second thing that has to be true that we're assuming is that we have independence between trials. So either the situation is completely independent, so that would be like flipping a coin, rolling a dice, something like that, where it absolutely, that probability of something happening doesn't change. Or if we are sampling without replacement, like picking something from a large group, which is usually what we're doing when we're taking a random sample, we have to make sure that that whole 10% rule passes. And we talked about this towards the very end of binomial, but the same thing applies here. So if sampling has been made without replacement, then the sample size, which is n, should be less than 10% of the population size. Or we can say it the other way and say that our population size needs to be at least 10 times the sample. When I referred to this back when we were learning binomial stuff, the end of last unit, my example went back to, talked about M&Ms. So if I was taking M&Ms from a bag of M&Ms and trying to find blue ones, my probability of getting a blue M&M is going to change when I take one out and don't replace it because there's less M&Ms in the bag and there's less blue ones. But if I have a really, really, really large bag of M&Ms that's got like 100,000 M&Ms in it, the probability is changing, but it's not changing a lot. It's not changing enough to make a big difference in my end result, my end probability. So the same thing applies here. If we're sampling without replacement, technically it's not independent, but we give ourselves a pass as long as n is less than 10% of the population size, because that basically means that probability is not changing enough to really matter. So that's our second assumption or condition that we have to check. And then our third one, and this is more of a condition, it's something you're checking as opposed to an assumption, which is something we assume. This is what we call the success failure condition, but basically this is the one that checks, is our distribution normal? Can we use a normal model to represent this sampling distribution for this situation? So again, this is something that came through lots of trial and error from statisticians before us. But basically what it came down to is that if n times p, remember n is the number or sample size, p is the probability, the proportion that's true for the whole group, the whole population, and then n times q. Q is just 1 minus p, by the way. It's just a shorthand. If both of those things are greater than or equal to 10, then we know our sampling distribution should look roughly normal. Again, that came from lots of trial and error. If it's something you want to play with, there is a great little online calculator that will kind of visualize that for you. So if I have a really small sample size and my p is pretty low, like 0.2, right, I end up with a distribution that's more skewed, that's not perfect. But if I make my sample size bigger, right, we can see that that distribution kind of becomes more normal. So there's a balance between n and p. As long as n times p and then n times 1 minus p, so same thing would happen on the other end. As long as both of those things are greater than 10, or that product is greater than 10, that distribution looks roughly normal, right? I'll show you one where if n is really small and p is kind of closer to the upper end of the distribution, then we end up with something that's skewed the other way, which is still not good. So we want n times p to be greater than 10 to kind of give us a distribution that is roughly normal. So those are things that we have to check. So we're going to jump into a problem. I'm going to go through one example in this video. It's what we did in class. And then I do have another example that I'm going to do in a separate video just so that you have extra practice if you would like it. So this example on this video right now is showing part of the steps because I forgot to set my transitioning right. That's a bell. Okay, a polling organization asked a simple random sample of 50 first-year college students. How far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home, so they're close to home. We're going to find the probability that in a random sample of 50 students, more than half of them go to college within 50 miles of home. One thing I want to point out that's really important in this unit, as opposed to in the last unit when we were dealing with binomial, it's all about how we phrase things and how we interpret what we're finding. So in the last unit in binomial, we were talking more about the number of successes, whereas in this one, we're talking about almost like the proportion of successes. So the proportion of students who live close to home, as opposed to the number of students who live close to home. So in sampling distributions right now, we're dealing with proportions. So I wanted to make that note, and then we'll come back to it. So number one, we're going to check, do our assumptions and conditions pass for this situation? So that first thing, random sample, is pretty easy because we were told that it is a random sample of first-year college students. So we're good there. That's not even something we have to assume. We know it to be true. So we're good on bias. We can pretty safely assume that there's not going to be bias in this situation, at least not sampling bias. The second assumption has to do with that 10%. In theory, we would be picking these 50 students, without replacement. So the probability of finding one who lives close to home versus far away is changing every time we pick a student. So what we have to assume here is that our sample size of 50 is less than 10% of all first-year college students everywhere. That would be our population, all first-year college students. And I think that's pretty safe to assume. That means there only needs to be 500 first-year college students anywhere. So I think that's a safe assumption, right? And then our third condition that we're checking is to make sure that the distribution that we're dealing with, our sampling distribution, is roughly normal. And the way we check that is, does n times p, which would be 50 is n times 0.35, because 35% of all the first-year college students live close to home. So that's p. That's our true proportion. So 50 times 0.35 is 17.5, which is bigger than 10. And then n times q, remember q is just 1 minus p, so 1 minus 0.35 is 0.65. So 50 times 0.65 is 32.5. Both of those are greater than 10, so that tells us our sampling distribution is going to be roughly normal. Not perfect, perhaps, in real sampling procedures, but it should be fairly close to normal. So now that we've checked that, that tells us, first of all, it's okay to continue. What we find from this answer should be fairly accurate, represent the situation well, but also we know it's okay for us to use a normal model, which again is going to make finding those probabilities a lot simpler since we know what to expect with the normal model. So our second step would be to go ahead and find the mean and standard deviation for the sampling distribution using our formulas. So this is what was already showing, but just to talk through, our mean is mu p hat equals p, which is just 0.35. That 35% of all, that is our true proportion for the entire population. That is p, according to this situation. We just happen to know that. And then our standard deviation from our sampling distribution is sigma p hat, is square root of p times 1 minus p over n. So square root of 0.35 times 1 minus 0.35, which is 0.65, over 50, which is our n, and that comes out to 0.067. Right, so just to give you an idea of what's happening here, we now know that this sampling distribution, if I were to take repeated samples of 50 students, just over and over again, take a random sample of 50 students from all over the US, and for each of those samples, calculate the proportion of them that attend college close to home, and then put all of those proportions in a new distribution, make a new graph out of them, that new graph of sample proportions will have a mean at roughly 0.35. It will have a standard deviation, the average distance from the mean for each proportion is 0.067. And then the shape of that graph would look roughly normal. So we now know what to kind of expect from a sample of size 50 in terms of the proportion of students who live within 50 miles of home. So now we're going to use that normal model to find a probability. So the probability we're finding is that for 50 students, more than half of them go to college within 50 miles of home. So the proportion we're trying to figure out about is half. What is the probability that our p hat, our sample proportion, so for a sample of 50 students, what's the probability that that sample proportion is greater than half? Okay. So we know that in our normal model, the mean is 0.35. So obviously greater than half is 0.5, is not going to be kind of super obvious or super typical. 0.5 is obviously higher than 0.35, but we know that it can happen. We know that not every sample of 50 students is going to have the exact same proportion who go to college close to home. So we're trying to find, where does 0.5 fit in on this? And that comes from finding a z-score. So z equals, remember I do my observed value. In this case, my observed value would be 0.5 because that is the number that I'm trying to determine the probability for. So 0.5 is my observed value minus 0.35 is my mean of this distribution. We got that in the last step. Divided by 0.067 is my standard deviation. Now, obviously, this is a rounded value. The very, very exact amazing thing to do would be to actually just put that whole thing in the calculator. So to actually say 0.5 minus 0.35 and then divide by and actually put square root of 0.35 times 0.65 divided by 50, because then we end up with something that is super, super exact and we're not rounding anywhere in between. Versus if I do it with the rounded value that I got from standard deviation, 0.067, right? I get something that's slightly different. It's not a huge amount different, so it's not the end of the world, and it would still be correct on an AP exam as long as you're showing your work like always. But that is just a quick little side note. So we get a z-score of about 2.24, which tells us that 0.5 as a proportion, as a sample proportion, is 2.24 standard deviations above the mean. So it's kind of far out there. It's not super typical, right? We're not in this kind of middle 68-ish% or even 95% of what's typical. It's pretty far away. So then once I have my z-score, I'm trying to find the probability that more than half. So I'm going to shade greater. And now I'm going to go to my z-table like always. I'm going to find the probability that our z-score is greater than 2.24. Remember, your z-table automatically gives you a less than. So once I find that number, I do need to subtract from 1. I didn't show that process on here. I just went straight to the answer. But that is what you would do if you were using your z-table. So 0.0125 is the probability of that happening. So interpreting that probability is something that we're going to do a lot more of in this unit and moving forward. So this is now a requirement to interpret the probability. So there is about a 1.25% chance, or a 0.0125 probability, that more than half of our sample of 50 students live within 50 miles of, go to college within 50 miles of home. That's worded wrong. So again, we're dealing with proportions here. Now, some of you might be thinking this seems really similar to what we did last unit. You could answer the same question with a binomial model, but answering it with a sampling distribution is going to lead more towards what we do later. But it is, in some ways, very similar to dealing with a binomial model. We're just taking it a little bit in a different direction. So again, key things to kind of keep in mind to remember is that we are dealing with proportion. So our observed value, our mean, our standard deviation are all in the context of a proportion. So that is why I have 0.5. Whereas with a binomial model, I would have said, half of 50 is 25. So I have to think about number of students versus proportion of students. On this type of problem, we're dealing with proportions. So just as a little key here, basic steps for solving these types of problems. So probability problems with sampling distributions. I'm going to go through the 4 things that we just did for that one example problem. First thing is we check the necessary assumptions and conditions, and we do have to write them or type them out on a free response question. We're not just thinking about them in our heads and then saying, okay, everything passes. We actually have to write them. I know. We're going to find the mean and standard deviation of the sampling distribution using those formulas. I'm going to then use the normal model, assuming that that condition passed in step 1. I'm going to use the normal model to find a probability, so find a z-score, use a z-table, etc. And then we interpret that probability by just writing a sentence explaining what that number means. All right, so there is one more example in here. I'm going to make a separate video going through that example and writing it out so that you have one more, and I will attach that as well. But that is all for this video. I will see you guys next time where we will discuss sampling distributions with means.